Good day, students. Myself, Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Tungar College, Bikaner. I welcome you all in my lecture series of Classical Mechanics, which is the first paper of MSc Previous Physics. As we have discussed in our previous lectures, that shape that the value of eccentricity epsilon, it decides the shape of orbit. And in our previous lectures we have shown that when epsilon is 1, then the orbital shape will be parabolic, and in the case of epsilon greater than 1 it will be hyperbola, and for epsilon to be less than 1, this is the condition when the conic shape is elliptical. And this is the most important case, as our earth is a planet and it revolves around sun, and the motion, orbital motion, is elliptical. That means it is a periodic motion. The other two situations, that means the case of epsilon 1 and epsilon greater than 1, hyperbola and parabola, they are non-periodic motion. Now, as now we will deal with the case in which the conic section is elliptical. That means epsilon less than 1 and the motion is periodic. So we will derive the time period of this elliptical motion. The time period of the elliptical motion is defined as ratio of total area to the area of total area of ellipse to the rate at which the area is swept out. That means tau, this is equal to area of the ellipse and the rate at which area is swept out. The rate is dA upon dt. So we have an ellipse which has a semi-major axis A and semi-minor axis as B. These two are the main axes of ellipse. Here the area of the ellipse in this condition will be equal to pi multiplied by A into B. Here in this diagram we have shown an orbit which is at a distance of radius vector r. Now I am considering this orbit with an inclination of angle d theta. Then this is my new position of orbital. So we have this in the shape of a triangle, and we know that area of triangle is half base into height. Here the height, it will be r d theta, as angle is equal to arc upon radius. So arc will be r into d theta. So my area dA will be half base into height. Half base is r and height is r d theta. Here we have divided by a term dt on the both sides. From this I get dA by dt to be half r square. D theta by dt is theta naught, half r square theta naught. Now we can see that Lagrangian in r theta coordinates is L is half m r dot square plus r square theta dot square minus VR. We know that the coordinate which do not appear in Lagrangian, it is a cyclic coordinate. Here it is evident that theta coordinate, it does not appear. So it will be a cyclic coordinate. only one generalized coordinate, that is r, appears in Lagrangian. Although we have two generalized coordinates r and theta, but since theta do not appear, it is a cyclic coordinate, and the momentum corresponding to a cyclic coordinate is constant. The generalized momenta is defined as p theta equal to delta L upon delta theta dot, and since it is a constant, I am denoting it by small l. From here I get mr square theta dot by differential of Lagrangian with respect to theta dot. So I get my theta dot as L upon mr square. Obtaining the value of theta dot, I am obtaining the value of dA upon dt, that is the rate of sweeping the area. So rate of sweeping the area was half r square theta dot, putting the value half r square theta dot is L by mr square. My dA by dt comes out to be L by 2m. So we have determined dA upon dt. Now, knowing the value of dA upon dt, I am going to find the period of elliptical motion. The time period of elliptical motion is defined as tau, which is area divided by dA by dt, and area is pi AB. dA by dt is L by 2m. So solving this, I get the time period of elliptical motion as 2 pi m AB divided by L. This is the time period of elliptical motion. We know that relation between the two axes, that means semi-major and semi-minor axis A and B, is B is equal to A under root 1 minus epsilon square. So from this I get my time period of elliptical motion as 2 pi m A, putting the value of B, A under root 1 minus epsilon square divided by L. In order to get it more simplified, I am taking square on both sides. So tau square comes out to be 4 pi square m square A4 1 minus epsilon square upon L square. As in our previous lectures, we have find the value of semi-major axis, which is A equal to P upon 1 minus epsilon square, and P is L square upon mk. So A comes out to be L square upon mk 1 minus epsilon square. Substituting the value of A, I get my tau square to be 4 pi square m divided by k multiplied by a cube. So tau square is directly proportional to a cube. This is our Kepler third law of motion, which states that the square of period of elliptical motion is proportional to cube of semi-major axis. A is the semi-major axis, and we can see that period of elliptical motion is independent of minor axis, which we denote as B. So we are able to derive all the three Kepler law of motion. Now I am summarizing all three laws which we have derived. The first law was planets move in ellipse with sun at one of foci. Our earth is a planet which moves around the sun And the condition we have already derived for elliptical motion is the condition that eccentricity it must be less than 1 and the motion will be a periodic motion. And the second law, it states that area swept by radius vector in equal times are equal. That is dA upon dt. This is constant. And the Kepler third law, which we have derived today, it states that the square of period of revolution is proportional to the cube of semi-major axis of ellipse. So these are the three important Kepler law of motion, and these law they are very applicable to understand the motion of earth which is moving around the sun. Thank you students for watching.